For thousands of years, humans have gazed at the stars and dreamed of distant worlds. Today, that dream is becoming reality. We stand on the brink of a new era in space exploration, where revolutionary missions will soon reveal planets beyond our solar system in ways we could never have imagined. Picture this: within our lifetime, we may finally answer the age-old question, are we alone in the universe? 30 groundbreaking missions are set to launch in the coming decades, each armed with cutting-edge technology that will transform how we discover and study exoplanets. These aren't just ordinary space telescopes, they're planet-hunting powerhouses capable of spotting Earth-like worlds light years away, analyzing their atmospheres for signs of life, and even capturing their direct images. Imagine seeing another blue marble floating in space, possibly harboring oceans, continents, and maybe even civilizations. The race to find habitable planets is heating up, with space agencies worldwide developing astonishing new tools, from starshades that block blinding starlight to interferometers combining multiple telescopes for unprecedented clarity. What we're about to explore will change everything we know about our place in the cosmos. Stay with me as we count down these 30 extraordinary missions that will redefine exoplanet science and potentially make the most important discovery in human history, proof that we're not alone. Now let's turn our attention to the first groundbreaking mission on our list, one that could revolutionize our search for life beyond Earth. NASA's Habitable Worlds Observatory represents a giant leap forward in our ability to study distant planets. This ambitious space telescope, currently planned for launch in the 2030s, is being designed with one extraordinary capability to directly photograph Earth-sized planets orbiting other stars. What makes this mission so special is its advanced coronagraph technology, a sophisticated starlight blocking system that acts like a cosmic visor. Imagine trying to spot a firefly next to a searchlight from miles away. That's the challenge of observing small planets near their bright host stars. The observatory's coronagraph will suppress that overwhelming starlight by a factor of 1 billion, allowing us to see the faint planetary gems hidden in the glare. But the Habitable Worlds Observatory won't just take pretty pictures. Its ultra-sensitive instruments will analyze the chemical composition of exoplanet atmospheres, hunting for telltale signs of life called biosignatures. We're talking about gases like oxygen, methane, and water vapor that could indicate biological activity. The telescope might even detect vegetation-like surface features through subtle color changes as planets rotate. This mission specifically targets planets in the habitable zone, that Goldilocks region where temperatures could allow liquid water to exist. By studying dozens of these promising worlds, the observatory could provide our first solid evidence that we're not alone in the universe. The technology behind this project is so advanced that it's being called the spiritual successor to the James Webb Space Telescope, potentially answering one of humanity's oldest questions within our lifetime. Moving beyond NASA's groundbreaking efforts, let's shift our gaze across the Atlantic to Europe's equally exciting contribution to exoplanet science. The European Space Agency's PLATO mission stands ready to expand our cosmic census in spectacular fashion. Scheduled for launch in 2026, this space observatory carries an ambitious goal to discover and characterize thousands of new worlds, with special focus on finding rocky planets like our own. What sets PLATO apart is its unique approach to planet hunting. Instead of directly imaging exoplanets, it employs an army of 26 ultra-sensitive cameras working in concert to detect the subtle dimming of stars as planets pass in front of them. This technique, called photometry, achieves precision so remarkable it could spot an exoplanet causing just a 1% dip in its star's brightness from hundreds of light years away. The mission's true power lies in its ability to pinpoint Earth-sized planets orbiting within their star's habitable zone, but PLATO won't stop at mere discovery. By carefully analyzing these planetary transits, scientists will determine each world's size, mass, and orbital characteristics with unprecedented accuracy. Some of these measurements will be so precise we'll even calculate a planet's density, revealing whether it's rocky like Earth or gaseous like Neptune. Plato's 6-year primary mission will monitor over 200,000 stars across vast stretches of the Milky Way. This cosmic survey could potentially identify dozens of Earth twins planets with similar size, composition, and temperature to our own world. The data may also reveal exotic planetary systems unlike anything in our solar system, challenging our understanding of how planets form and evolve. What makes this mission particularly exciting is its timing. Plato discoveries will create the perfect target list for follow-up observations by NASA, a Habitable Worlds Observatory, and other next-generation telescopes. Together, these missions could finally answer whether planets capable of supporting life are cosmic rarities or common occurrences in our galaxy. The stage is being set for discoveries that may redefine humanity's place in the universe. Now let's turn our attention to an ambitious vision that could redefine our search for life beyond Earth. NASA's Large Ultraviolet Optical Infrared Surveyor, or LUVOIR, represents one of the most powerful space telescope concepts ever imagined. This behemoth of astronomy, currently planned for potential launch in the 2040s, would dwarf even the James Webb Space Telescope in both size and capability. At its core, LUVOIR is designed to answer one of humanity's oldest questions: are we alone in the universe? With a primary mirror stretching up to 15 meters across, this telescope would possess resolution so sharp it could directly image Earth-sized exoplanets around nearby stars. Imagine being able to see another pale blue dot in the cosmos, not just detect its presence through indirect methods. The telescope's name reveals its incredible versatility. By observing across ultraviolet, optical, and infrared wavelengths simultaneously, LUVOIR could analyze exoplanet atmospheres in unprecedented detail. It would search for telltale signs of life like oxygen, methane, and even artificial pollutants that might indicate technological civilizations. The instrument could potentially detect seasonal changes on distant worlds, cloud patterns, and surface features that hint at oceans or continents. What makes LUVOIR particularly exciting is its potential to study dozens of potentially habitable worlds in our cosmic neighborhood. Unlike missions focused on discovery, this observatory would conduct in-depth investigations of planets we've already found. Scientists could compare atmospheric compositions across different planetary systems, looking for patterns that might reveal how common life-friendly environments truly are. The technological challenges are immense. LUVOIR would require advanced coronagraphs to block starlight millions of times brighter than the planets we want to see. Its instruments would need sensitivity to detect molecules present in just trace amounts in alien atmospheres, and the entire structure would need to unfold perfectly in space, with mirror segments aligning to nanometer precision. If funded and built, this observatory could provide our first definitive evidence of life beyond Earth within our lifetime. The data might reveal not just microbial life, but potentially complex biospheres on worlds orbiting other stars. As we wait for this potential game-changer, one thing is certain: the 2040s could bring revelations that transform our understanding of life's place in the cosmos. Shifting our gaze to the cold, dusty nurseries of alien worlds, the Origin Space Telescope offers a completely different window into exoplanet science. While LUVOIR focuses on visible light and nearby planets, this groundbreaking far-infrared observatory will peer into the frigid regions where planets are born, revealing secrets about how worlds like ours come into existence. The Origin Space Telescope specializes in detecting heat signatures from objects just a few degrees above absolute zero. This lets it study the raw materials of planet formation, vast disks of gas and dust swirling around young stars. Within these cosmic construction zones, the telescope could spot the building blocks of future ocean worlds or rocky planets, mapping out where water, ice, and complex organic molecules are concentrated. What makes Origins truly revolutionary is its ability to analyze the atmospheric chemistry of mature exoplanets in unprecedented detail. While other telescopes struggle to identify molecules in exoplanet atmospheres, Origins' far-infrared vision could detect the chemical fingerprints of water vapor, carbon dioxide, and even more complex organic compounds. These detections wouldn't just tell us what's in an alien atmosphere, they'd reveal how these molecules interact, potentially showing us active atmospheric processes like rain cycles or chemical weathering. The telescope's most exciting capability might be hunting for biosignatures in unexpected places. While most missions look for oxygen as a sign of life, Origins could search for chemical imbalances that don't make sense without biological activity. Imagine detecting methane that shouldn't exist alongside certain other gases, or finding complex organic molecules distributed in patterns that suggest biological origin. Origins would complement missions like LUVOIR perfectly. While one shows us what exoplanets look like, the other reveals what they're made of and how they formed. Together, they could answer whether planets with Earth-like chemistry are cosmic accidents or common occurrences. As we piece together the story of planet formation across our galaxy, the Origins Space Telescope might finally show us how frequently the universe creates worlds capable of nurturing life. Now let's turn our attention to a mission that takes teamwork to cosmic heights. The Large Interferometer for Exoplanets or Life represents a bold new approach to studying distant worlds. Led by the European Space Agency, this mission doesn't rely on a single telescope. Instead, it combines the power of multiple spacecraft working in perfect harmony to unlock secrets no solo instrument could reveal. Here's how this cosmic symphony works. Life will deploy several free-flying telescopes that precisely coordinate their observations. By carefully combining the light they collect, these spacecraft create what's essentially a giant virtual telescope with unprecedented resolution. This technique, called interferometry, allows life to pick apart the faint glow of exoplanet atmospheres with astonishing detail, like distinguishing individual instruments in an orchestra from light years away. What makes life truly special is its focus on Earth-like worlds. While other missions might spot gas giants easily, life interferometric precision targets smaller, rocky planets in habitable zones. It could analyze their atmospheric composition molecule by molecule, searching for water vapor, carbon dioxide, methane, and even potential biosignatures like oxygen. The mission's sensitivity might detect seasonal changes or weather patterns on these distant worlds. Imagine the possibilities. Life could study dozens of potentially habitable exoplanets, comparing their atmospheres to Earth's at different stages of our planet's history. Did Mars once have a thicker atmosphere? What did Earth's air look like before plants filled it with oxygen? By observing exoplanets at various evolutionary stages, life might help us understand how atmospheres and life develop over cosmic timescales. This mission builds on decades of interferometry experiments but scales them up for revolutionary science. While technical challenges remain in keeping multiple spacecraft perfectly aligned across vast distances, the payoff could redefine our search for life. Life wouldn't just find planets, it would study their atmospheres with enough precision to ask whether they're merely habitable or perhaps already inhabited. As we wait for life proposed launch in the 2030s, one thing is clear. This mission represents a giant leap in our ability to not just discover exoplanets, but to truly understand them. By combining the light from multiple telescopes, we might finally combine the pieces of the ultimate puzzle. Are we alone in the universe? Now let's zoom in on our cosmic backyard with a mission that's turning its gaze toward our nearest stellar neighbors. The Telescope for Orbit Locus Interferometric Monitoring of our Astronomical Neighborhood, or TOLOMAN, has one clear target in mind: Alpha Centauri, the star system just over 4 light-years away. What makes Ptolemy unique is its razor-sharp focus on precision. Unlike missions that scan thousands of distant stars, this one hones in on our closest stellar companions with micro-arcsecond astrometry, a technique so sensitive it could detect a planet's gravitational wobble down to the width of a human hair seen from a mile away. Imagine the potential. If rocky planets orbit Alpha Centauri's stars, Ptolemy could spot them by measuring the tiniest shifts in starlight caused by their gravitational pull. This isn't just about finding any exoplanet, it's about searching for worlds that could one day be within reach of robotic probes or even human exploration. The mission's name itself hints at its ambition. Ptolemy derives from the ancient Arabic name for Alpha Centauri, reflecting humanity's long fascination with these nearby stars. By focusing on our celestial doorstep, this mission bridges the gap between exoplanet science and interstellar exploration. Here's why that matters. Discovering a habitable world next door would revolutionize our understanding of planetary formation and the prevalence of life. It could also become the prime target for future missions like Breakthrough Starshot, which aims to send tiny probes hurtling toward Alpha Centauri at a fraction of light speed. Ptolemy's approach is deceptively simple yet groundbreaking. Instead of relying on massive telescopes, it uses a compact, specially designed instrument optimized for extreme precision on a single star system. This lean design could pave the way for more targeted exoplanet hunts, proving that sometimes the most exciting discoveries come from looking closely at what's right in front of us. As we anticipate Ptolemy's launch in the coming years, one thing is certain. This mission reminds us that the search for other worlds isn't just about the far reaches of space. Sometimes the answers we seek might be hiding in plain sight, waiting for us to look with just the right level of precision. Shifting our gaze to another game-changing mission, let's talk about the Nancy Grace Roman Space Telescope, formerly known as LUVOIR. This powerhouse of a telescope is set to redefine how we study exoplanets, especially gas giants and Neptune-like worlds. What sets the Roman Space Telescope apart is its cutting-edge coronagraph, a device designed to block out the blinding light of stars, allowing faint orbiting planets to shine through. Think of it like using your hand to shield your eyes from the sun to spot an airplane in the sky. But this isn't just any coronagraph. It's one of the most advanced ever built, capable of directly imaging planets that would otherwise be lost in their star's glare. The telescope's primary targets, gas giants and ice giants, planets similar to Jupiter or Neptune. By studying these worlds, scientists hope to unlock secrets about how planetary systems form and evolve. But here's the real kicker. The technology being perfected here isn't just for spotting big planets. It's laying the groundwork for future missions to detect something far more tantalizing: Earth-like worlds. Imagine this: the Roman Space Telescope's coronagraph will act as a proving ground for techniques that could one day help us photograph a pale blue dot orbiting another star. Every gas giant it images, every Neptune-like world it analyzes, brings us one step closer to refining the tools needed to find a true Earth twin. And the timing couldn't be better. Slated for launch in the next few years, the Roman Space Telescope will complement other missions like the Habitable Worlds Observatory, creating a domino effect of discovery. First, we master imaging larger planets. Then, we turn that knowledge towards smaller, rocky worlds in the habitable zone. This mission is more than just a telescope. It's a bridge, a crucial link between where we are now and the day we finally spot another planet like ours. So while it might focus on giants for now, its legacy will be measured in the Earths we find tomorrow. Now, let's turn our attention to a mission that's all about peeling back the layers of distant worlds, literally. The European Space Agency's Ariel mission, short for Atmospheric Remote Sensing Infrared Exoplanet Large Survey, is set to launch in 2029 with one ambitious goal: to study the atmospheres of over 1,000 exoplanets. Unlike missions that focus on imaging planets directly, Ariel will take a different approach. It's designed to analyze the chemical makeup and climate of these distant worlds by observing the light that filters through their atmospheres as they pass in front of their host stars. Picture it like holding a prism up to a distant light source, except instead of seeing colors, scientists will decode the fingerprints of gases like water vapor, carbon dioxide, and even methane. What makes Ariel so groundbreaking is its sheer scale. No mission before it has attempted to survey such a vast number of exoplanet atmospheres, covering everything from scorching hot Jupiters to cooler, smaller worlds. This treasure trove of data will help researchers answer fundamental questions. Are there common patterns in how planets form? How do their atmospheres evolve over time? And perhaps most intriguingly, could any of them hint at conditions suitable for life? The mission's infrared capabilities are key. Infrared light is ideal for detecting heat and the chemical signatures of molecules, making it perfect for studying planetary atmospheres. Ariel will essentially act as a giant cosmic weather station, cataloging temperatures, cloud formations, and even wind patterns across a diverse range of exoplanets. But Ariel isn't just about collecting data, it's about context. By comparing atmospheres across different types of planets, scientists hope to build a universal framework for understanding planetary systems, one that could even shed light on our own solar system's history. As we inch closer to 2029, Ariel stands as a testament to how far exoplanet science has come. It's not just about finding planets anymore. It's about understanding them, unlocking the stories written in their skies. And with each atmosphere it deciphers, Ariel will bring us closer to answering one of humanity's oldest questions: are we alone in the universe? Now imagine trying to spot a firefly next to a spotlight. That's the challenge of finding Earth-like exoplanets hidden in the glare of their host stars. Enter NASA Habitable Exoplanet Observatory, or HAB-X, a revolutionary concept designed to solve this very problem with a dazzling piece of engineering, the starshade. Unlike traditional telescopes that rely solely on advanced optics, HAB-X pairs a powerful space telescope with a separate, flower-shaped starshade flying tens of thousands of kilometers ahead of it. This starshade acts like a cosmic visor, precisely positioned to block the blinding light of a star, allowing the telescope to capture the faint glow of orbiting planets. Think of it as using your hand to shield your eyes from the sun to spot something delicate in the distance, except on an interstellar scale. The magic lies in the starshade's design. Its intricate petals scatter starlight in a way that minimizes diffraction, creating a deep shadow where the telescope can hunt for exoplanets. This technology isn't just about blocking light. It's about revealing worlds that would otherwise remain invisible. HAB-X could directly image Earth-sized planets in habitable zones, the Goldilocks regions where liquid water might exist, and analyze their atmospheres for signs of life like oxygen or methane. But HAB-X's ambitions don't stop there. The mission aims to study dozens of nearby stars, targeting systems most likely to host rocky, Earth-like planets. By combining its starshade with a coronagraph, an internal instrument that further suppresses starlight, HAB-X would cross-verify its discoveries, reducing the risk of false positives. This dual approach makes it one of the most promising concepts for finding truly habitable worlds. What sets HAB-X apart is its potential to answer a question that's haunted us for centuries: is there another Earth out there? If funded, this mission could launch as early as the 2030s, offering humanity its first clear portraits of planets that might resemble our own. And with each image, we'd take another step toward understanding whether life exists beyond our solar system, or if we're alone in the cosmic ocean. The starshade isn't just a tool. It's a gateway to the unknown, pushing the boundaries of what's possible in our search for habitable worlds. And as HAB-X moves from concept to reality, It reminds us that the future of exoplanet discovery isn't just about seeing farther, it's about seeing clearer. Now, shifting our gaze from starshades to the vast cosmic map, let's turn our attention to NASA's SPHEREX mission. This isn't just another telescope, it's a cosmic cartographer on a grand scale, designed to scan the entire sky in infrared light, not once but 4 times over its 2-year mission. Picture it as creating a detailed, multi-layered atlas of the universe, where every snapshot reveals hidden secrets about galaxies, stars, and even the atmospheres of distant exoplanets. What makes SPHEREX truly special is its ability to peer into the infrared spectrum, a wavelength range invisible to our eyes but rich with information. By analyzing the faint glow of celestial objects in infrared, SPHEREX can uncover the chemical fingerprints of exoplanet atmospheres. Imagine studying the light filtering through an alien world's air, breaking it down like a prism to detect molecules like water vapor, carbon dioxide, or even methane, clues that could hint at habitability or perhaps life itself. But SPHEREX isn't just about exoplanets. Its broader mission is to map hundreds of millions of galaxies, some so distant their light has traveled billions of years to reach us. This will help scientists unravel the universe's history, from its earliest moments to the sprawling cosmic web we see today. And here's the kicker: by surveying the sky so thoroughly, SPHEREX might stumble upon unexpected discoveries, new exoplanets, mysterious cosmic phenomena, or even anomalies that challenge our understanding of physics. Slated for launch no earlier than 2025, SPHEREX represents a unique blend of exploration and detective work. It won't just take pretty pictures. It'll decode the universe's hidden language, one infrared signal at a time. And while it scans the heavens, it'll quietly advance our search for other Earths, proving once again that the tools we build to study the cosmos often reveal far more than we ever imagined. So as we wait for SPHEREX to begin its celestial survey, remember this: every time we map the unknown, we're not just charting stars, we're drawing closer to answering the ultimate question. Are we alone? And with missions like SPHEREX, that answer might be closer than we think. Now, stepping into the realm of ultraviolet exploration, let's uncover the potential of CETUS, a mission that could revolutionize how we study exoplanet atmospheres. Unlike telescopes that focus on visible or infrared light, CETUS is designed to capture the universe in ultraviolet, a wavelength range that holds crucial clues about the survival of planetary atmospheres. Think of CETUS as a cosmic detective specializing in tracking atmospheric escape, the process where gases like hydrogen and oxygen leak from a planet's atmosphere into space. This might sound like a niche detail, but it's actually a game changer for habitability. If an exoplanet loses too much of its atmosphere, especially water vapor, it could become a barren wasteland, no matter how perfectly positioned it is in the habitable zone. CETUS aims to measure these escape rates with unprecedented precision, helping us understand which worlds might truly hold onto the conditions needed for life. But CETUS isn't just about doom and gloom. By analyzing ultraviolet light, it can also detect the presence of ozone, a molecule often linked to biological activity. On Earth, our ozone layer protects life from harmful solar radiation. Finding a similar shield on another world would be a tantalizing hint that life might exist there too. Plus, CETUS could study the violent flares of host stars, which can strip away atmospheres over time, giving us a clearer picture of how star-planet interactions shape a world's fate. Still in the proposal stage, CETUS represents a bold step forward in exoplanet science. It's not just about finding planets, it's about understanding whether they can keep their life-sustaining environments over billions of years. And with its ultraviolet eyes, CETUS might finally answer one of astronomy's biggest questions: which exoplanets are truly built to last? As we look ahead, missions like CETUS remind us that the search for life isn't just about discovering new worlds. It's about peeling back the layers of their atmospheres, one wavelength at a time, to uncover the stories they've been hiding all along. Now, shifting our gaze to the icy cradles of newborn worlds, let's revisit the Origin Space Telescope with a fresh perspective. While its primary mission focuses on exoplanet atmospheres, OST's secondary objectives are just as thrilling, peering into the chaotic nurseries where planets are born. Imagine a cosmic chemist sifting through the frozen ingredients of protoplanetary disks, the swirling rings of gas and dust around young stars. OST's far-infrared vision is uniquely suited to spot water ice, carbon monoxide, and even complex organic molecules like methanol in these disks. Why does this matter? Because these icy building blocks are the raw materials for future planets and possibly life. By mapping their distribution, OST could reveal how water gets delivered to budding worlds. Picture this, a fledgling Earth-like planet forming in the habitable zone. If OST detects water ice in its birth disk, it's a strong hint that the planet might inherit oceans just as Earth did. But the telescope's reach goes further. It could uncover snow lines, the boundaries where different gases freeze out, shaping where rocky planets versus gas giants emerge. OST's observations might also solve a long-standing puzzle: how organic molecules survive the violent chaos of planet formation. These molecules, essential for life, are fragile, yet they're found everywhere from comets to meteorites. By catching them in the act of embedding into young planets, OST could show us how the seeds of life spread across the cosmos. This mission isn't just about snapping pictures of distant disks. It's about decoding the recipes that turn stardust into living worlds. And with OST's unmatched sensitivity, we're not just watching planet formation, we're uncovering the hidden blueprints of cosmic life itself. As we piece together these clues, one thing becomes clear: the story of exoplanets doesn't start with a fully formed world. It begins in the frosty shadows of a star's cradle, where OST is poised to rewrite the textbook on how planets, and perhaps life, come to be. Now, let's turn our attention from the icy cradles of planet formation to the fiery hearts of stars themselves, because sometimes to understand a world, you need to study the sun that gives it life. Enter the LINX X-ray Observatory, a mission that flips the script on exoplanet research. Instead of staring directly at distant planets, LINX will train its sharp X-ray vision on their host stars, uncovering secrets that could make or break habitability. Here's the twist: a star's X-ray activity tells us far more than just how hot it burns. Frequent, violent flares and coronal mass ejections, those eruptions of charged particles, can strip away a planet's atmosphere or bathe its surface in deadly radiation. LINX will map these outbursts with unprecedented clarity, revealing which stars are cosmic neighbors you'd actually want to live next to. Picture a red dwarf star, small but temperamental, unleashing flares hundreds of times stronger than anything our sun produces. If an Earth-like planet orbits too close, LINX could show us whether its atmosphere stands a chance, or if it's being slowly cooked into a barren rock. But the observatory's insights go beyond doom and gloom. By studying the X-ray glow of young stars, LINX might spot the telltale signs of planet formation in action. Hot gas spiraling into gaps in protoplanetary disks. That's likely the gravitational fingerprint of a baby planet carving its path. And for older systems, subtle X-ray dimming could hint at transiting exoplanets too faint for other telescopes to catch. LINX's real power lies in connecting the dots. A star's radiation history shapes everything from a planet's magnetic field to the chemistry of its oceans. By decoding these X-ray clues, we're not just cataloging exoplanets, we're grading them on cosmic livability. So while LINX never directly images a single alien world, it might just tell us which ones are worth a closer look. Up next, we'll push the boundaries even further beyond our solar system's edge, to a mission that dares to dream of interstellar flybys. But for now, LINX reminds us, sometimes the key to finding life lies in reading the stars themselves. Now, let's take a leap beyond the familiar boundaries of our solar system, because the next mission on our list isn't just about observing distant worlds from afar. It's about reaching out to them. Meet the interstellar probe, a bold concept that could one day send a spacecraft hurtling into the vast unknown, venturing farther than any human-made object has gone before. This isn't just another telescope or orbital mission. The interstellar probe is designed to break free from the sun's gravitational grip and journey into interstellar space, targeting nearby star systems within a few centuries. Think of it as a message in a bottle, but instead of floating on the ocean, it's sailing through the cosmic void, carrying humanity's curiosity to the stars. The probe's primary goal, to fly by exoplanets in our stellar neighborhood like Proxima Centauri b, and capture data we could never gather from light years away. Imagine close-up images of an alien world's surface, detailed scans of its atmosphere, or even signs of weather patterns, all beamed back to Earth decades or centuries after launch. It's a long-term investment, but one that could redefine our understanding of habitable worlds beyond the sun. Of course, the challenges are staggering. The distances are mind-bending, and even at incredible speeds, reaching another star would take generations. But here's the exciting part. Advances in propulsion, like nuclear or laser-driven sails, could slash travel times dramatically. And while the probe itself might not survive the journey, its data could give future civilizations their first true glimpse of an exoplanet up close. What makes this mission so revolutionary isn't just the science, it's the audacity. The interstellar probe represents humanity's first real step toward becoming an interstellar species, not with warp drives or sci-fi tech, but with patience, ingenuity, and the courage to think in timescales longer than a single lifetime. Up next, we'll shift gears to something even more futuristic, a project that aims to send tiny probes to the stars at a fraction of the speed of light. But for now, the interstellar probe stands as a testament to our enduring dream, to touch the cosmos one star at a time. Now, let's turn our attention to a mission that sounds like it's straight out of science fiction, but it's very real, and it could revolutionize how we explore the stars. Enter Breakthrough Starshot, an audacious plan to send tiny, lightweight probes to our nearest stellar neighbor, Alpha Centauri, at an astonishing 20% the speed of light. Unlike traditional spacecraft that take decades or even centuries to reach another star, these nano-probes could make the journey in just over 20 years. How? By harnessing the power of light itself. The idea is to equip the probes with ultra-thin, reflective sails, then blast them with powerful ground-based lasers. This laser propulsion system would accelerate them to unprecedented speeds, allowing them to zip past Alpha Centauri's exoplanets like Proxima Centauri b and snap close-up images before sailing onward into the cosmos. The potential here is staggering. For the first time, we could get a detailed look at an exoplanet's surface features, weather patterns, or even signs of habitability, all from just a flyby. And because these probes are so small and lightweight, they'd be relatively inexpensive to produce, making interstellar exploration more feasible than ever before. Of course, the challenges are immense. The laser array required would need to be the most powerful ever built, and the probes would have to survive decades of travel through interstellar space, dodging cosmic dust and radiation. But if successful, Breakthrough Starshot could deliver our first real glimpse of another habitable world by the middle of this century, far sooner than any other mission on the horizon. What makes this project so thrilling isn't just the science, it's the sheer boldness of the vision. Instead of waiting for futuristic warp drives or generational ships, Starshot offers a tangible, near-term path to the stars. It's a reminder that the next giant leap in exoplanet exploration might not come from bigger telescopes, but from thinking smaller and moving faster. Up next, we'll explore another groundbreaking concept, one that could detect alien civilizations not by their atmospheres, but by their city lights. But for now, Breakthrough Starshot stands as a beacon of what's possible when we dare to dream at the speed of light. Now, let's shift gears to a mission that takes exoplanet hunting to an entirely new level, one that doesn't just look for signs of life but searches for signs of intelligence. Meet the Colossus Telescope, a groundbreaking ground-based concept designed to spot something extraordinary, city lights or even megastructures on distant exoplanets. Imagine pointing a telescope at a far-off world and detecting the faint glow of artificial light, evidence of a civilization that, like ours, has illuminated its nights. That's the bold vision behind Colossus. Unlike most telescopes that focus on atmospheric gases or surface conditions, this one would hunt for the unmistakable fingerprints of advanced technology. Here's how it could work. Colossus would rely on an array of massive mirrors working together to capture the faintest traces of light reflected off exoplanets. By analyzing subtle changes in brightness, scientists could distinguish between natural sources like sunlight bouncing off oceans and artificial ones like sprawling cities or massive solar panels. Even more intriguing, it might spot megastructures, hypothetical constructs like Dyson spheres, which advanced civilizations could build to harness a star's energy. The challenges enormous. Detecting something as dim as city lights across light years would require a telescope with unprecedented sensitivity, likely spanning hundreds of meters. Atmospheric interference and light pollution would also pose hurdles. But if successful, Colossus could answer one of humanity's oldest questions: are we alone? What makes this concept so compelling is its audacity. Instead of waiting for aliens to send signals, we'd actively search for their footprints on distant worlds. It's a reminder that the next breakthrough in exoplanet science might not come from spotting a habitable planet, but from spotting one that's already inhabited. Up next, we'll dive into another innovative mission, one that aims to democratize exoplanet discovery with a fleet of low-cost, high-impact telescopes. But for now, Colossus stands as a thrilling example of how far our search for cosmic neighbors could go. Now, let's turn our attention to a mission that flips the script on traditional exoplanet hunting by making it more affordable and accessible than ever. Enter the Nautilus Space Observatory, an ambitious project that plans to deploy an array of low-cost telescopes with one big goal: to scan millions of stars for transiting exoplanets. What sets Nautilus apart is its revolutionary diffractive optics. Unlike conventional telescopes that use bulky lenses or mirrors, these telescopes rely on lightweight, flat lenses etched with intricate patterns. These patterns bend light in precise ways, allowing Nautilus to capture sharp images while keeping costs and weight dramatically lower. This breakthrough means we could launch dozens or even hundreds of these compact telescopes into space, creating a vast network with unparalleled coverage. The mission's strategy is simple but powerful. By spreading these telescopes across different orbits, Nautilus could monitor the same star from multiple angles, reducing false positives and catching fleeting planetary transits that a single telescope might miss. Over time, this swarm could survey millions of stars, vastly expanding our catalog of known exoplanets, including Earth-sized worlds in habitable zones. But the real game changer here is scalability. Traditional space telescopes often take decades and billions of dollars to build. Nautilus, with its modular design and cost-effective tech, could be deployed faster and updated more easily, keeping pace with rapid advancements in exoplanet science. Of course, challenges remain. Diffractive optics are still being refined, and coordinating a fleet of telescopes demands precision. Yet if successful, Nautilus could democratize exoplanet discovery, making it a team effort not just for space agencies but for scientists and universities worldwide. Up next, we'll explore a mission that once seemed like a dream but continues to inspire the next generation of planet hunters. But for now, Nautilus reminds us that sometimes the future of exploration isn't about building one giant telescope, it's about launching many small ones, working together to unlock the universe's secrets. Now, let's take a step back and revisit a mission that never made it to launch, but left an indelible mark on exoplanet science. Meet EXEED, the Exoplanetary Circumstellar Environments and Disk Explorer. Though it was cancelled in 2015, this mission's bold vision for studying planet-forming disks continues to shape how we explore the birthplaces of new worlds. EXEED was designed to peer into the swirling clouds of gas and dust around young stars where planets are born. Using a cutting-edge coronagraph, it aimed to block out starlight with unprecedented precision, revealing the faint glow of these protoplanetary disks in stunning detail. Scientists hope to capture snapshots of planets in the making, watching as dust grains clump together, forming the building blocks of future solar systems. What made EXEED special was its focus on dynamics. Instead of just cataloging disks, it sought to understand how they evolve over time. By observing the same systems repeatedly, it could track changes in disk structures, spot gaps carved by newborn planets, and even detect signs of migrating worlds, key clues to how planetary systems like ours come to be. Though budget cuts ended EXEED before liftoff, its legacy lives on. The mission's ambitious goals directly influenced later projects, like the James Webb Space Telescope's disk studies and the upcoming Habitable Worlds Observatory. Its coronagraph technology also paved the way for starlight suppression techniques now considered essential for imaging Earth like exoplanets. EXEED's story reminds us that even missions that don't fly can propel science forward. Its ideas continue to inspire, proving that sometimes the boldest blueprints become the foundation for tomorrow's discoveries. Up next, we'll shift gears to a small SAT mission tackling one of exoplanet science's trickiest challenges, but for now, EXEED stands as a testament to how visionary thinking outlasts any single mission. Now, let's turn our attention to a mission that's tackling one of the biggest headaches in exoplanet research, the Pandora mission. This small SAT project might be compact in size, but its ambitions are anything but small. Pandora's goal: to untangle the messy signals from stars and planets, giving us a clearer picture of what's really happening in those distant atmospheres. Here's the problem: when we study exoplanet atmospheres, the light we're analyzing isn't just from the planet, it's mixed with the light of its host star. Stellar activity, like flares or sunspots, can mimic or obscure the chemical signatures we're trying to detect. That means a planet's atmosphere might look like it has water or methane when it's actually just the star playing tricks on us. Pandora is designed to cut through that noise. How? By observing the same star and its planet simultaneously in both visible and infrared light. This dual wavelength approach lets scientists separate the star's behavior from the planet's true atmospheric signals. Think of it like tuning out static on a radio. Pandora helps us hear the music of exoplanet atmospheres without the interference. Slated for launch in the mid-2020s, Pandora will focus on 20 or more star systems, targeting small, cool stars known as M-dwarfs. These stars are prime targets for finding rocky, Earth-sized planets, but their frequent flares make atmospheric studies extra challenging. Pandora's data could be the key to confirming whether these worlds have the right ingredients for life or ruling them out entirely. What makes Pandora especially exciting is its cost-effective design. As a small SAT, it proves that big discoveries don't always require billion-dollar budgets. By refining our ability to study exoplanet atmospheres, Pandora could pave the way for future missions to identify unmistakable signs of life beyond our solar system. Up next, we'll explore another mission hunting for Earth's twin, but for now, Pandora reminds us that sometimes the smallest tools can solve the biggest puzzles in our search for habitable worlds. Shifting our gaze to the east, China is stepping into the exoplanet hunt with a mission that could redefine our search for Earth-like worlds. Meet Earth 2.0, also known as the ET mission, set to launch in 2026. This ambitious project takes inspiration from NASA Kepler, but with a crucial upgrade: unmatched precision in detecting planets within habitable zones. Here's what sets Earth 2.0 apart. While Kepler gave us a treasure trove of exoplanets, many were gas giants or worlds too close to their stars. Earth 2.0 is laser-focused on finding true Earth twins rocky planets orbiting at just the right distance for liquid water. To do this, it'll monitor around 1.2 million stars using ultra-sensitive photometry, spotting the faintest dips in starlight caused by transiting planets. But the real game-changer is its targeting strategy. Earth 2.0 will prioritize Sun-like stars, unlike missions that focus on dimmer M-dwarfs. Why? Because these stars offer the best analogs to our own solar system, raising the odds of finding planets with Earth-like conditions. The mission's instruments are fine-tuned to detect planets as small as 0.8 Earth radii, a leap in precision that could reveal worlds nearly identical to ours. China's investment in this mission signals its growing role in space science. With a planned 4-year baseline operation, Earth 2.0 could catalog thousands of new exoplanets, narrowing down the most promising candidates for follow-up atmospheric studies. Imagine the excitement if it finds a planet with Earth-size orbit and even a similar atmosphere. As we look ahead, Earth 2.0 reminds us that the search for habitable worlds is a global effort. Next up, we'll see how ground-based telescopes are joining this cosmic detective work. But for now, China's mission stands as a beacon of what's possible when technology and ambition align in the hunt for our planetary twins. Now let's turn our attention to the ground, where a powerful new instrument is set to revolutionize our understanding of exoplanet atmospheres without ever leaving Earth. Meet ANDES, the Atmospheric Remote Sensing Infrared Exoplanet Large Survey, a cutting-edge tool designed for the Extremely Large Telescope, or ELT. This isn't just another telescope, it's a game-changer for studying distant worlds from right here on our planet. What makes ANDES special is its ability to analyze the atmospheres of exoplanets in stunning detail. While space telescopes like James Webb have given us incredible insights, ground-based instruments like ANDES bring their own advantages. Mounted on the ELT, which boasts a mirror spanning 39 meters, ANDES will capture light from exoplanets with unprecedented clarity. Its infrared capabilities allow it to detect key molecules like water vapor, carbon dioxide, and even potential biosignatures like oxygen or methane. But here's where it gets even more exciting. ANDES isn't just observing giant gas planets, it's fine-tuned to study smaller, rocky worlds in habitable zones. By analyzing the starlight filtering through an exoplanet's atmosphere during transits, it can reveal the chemical makeup and even clues about weather patterns or surface conditions. Imagine confirming an Earth-like atmosphere on a distant world without sending a single probe into space. One of ANDES' most ambitious goals is to study Proxima Centauri b, our closest known exoplanet neighbor. Located just over 4 light-years away, this rocky world orbits within its star's habitable zone. With ANDES, scientists hope to determine whether its atmosphere could support liquid water or even life. The ELT's location in Chile's Atacama Desert, with its clear skies and minimal light pollution, makes it the perfect home for ANDES. Scheduled to begin operations in the late 2020s, this instrument will complement space-based missions, offering a ground-level perspective that could answer some of astronomy's biggest questions. As we push the boundaries of exoplanet science, ANDES proves that some of the most groundbreaking discoveries might come from right here on Earth. Up next, we'll revisit a shelved mission whose legacy continues to inspire today's most ambitious projects. Now, let's take a step back in time to explore a mission that never flew but left an indelible mark on exoplanet science: the European Space Agency's Darwin project. Conceived in the late 1990s, Darwin was ahead of its time, envisioning a fleet of space telescopes working together as an interferometer to directly image Earth-like exoplanets and analyze their atmospheres. Though budget constraints led to its cancellation in 2007, Darwin's bold ideas continue to shape today's most ambitious missions. What made Darwin revolutionary was its plan to combine the light from multiple telescopes, effectively creating a virtual observatory with the resolution of a single massive instrument. This technique, known as nulling interferometry, would have allowed Darwin to block out the blinding glare of host stars, revealing faint, rocky planets orbiting them. The goal, to detect biosignatures like oxygen, water vapor, and methane, key indicators of potential life. Decades later, Darwin's legacy lives on. Missions like LIFE, the Large Interferometer for Exoplanets, and NASA LUVOIR concept owe much to Darwin's pioneering vision. LIFE, for instance, plans to use a similar interferometry approach to study exoplanet atmospheres with unparalleled precision, while LUVOIR colossal mirror design draws inspiration from Darwin's emphasis on high-resolution imaging. One of Darwin's most forward-thinking aspects was its focus on mid-infrared observations. This wavelength range is ideal for spotting thermal emissions from exoplanets, making it easier to identify habitable conditions. Today, instruments like the James Webb Space Telescope and future projects like the Origin Space Telescope are prioritizing mid-infrared for the same reason, proving Darwin's foresight. While Darwin never reached the launch pad, its influence is undeniable. It challenged engineers to think bigger, proving that the search for life beyond Earth demands bold, collaborative technology. As we look to missions like LIFE and LUVOIR, we're not just building telescopes, we're fulfilling a vision that began with Darwin. Next up, we'll revisit another early concept that could still transform how we see distant worlds, the New Worlds mission. Now, shifting our gaze to another visionary idea, let's revisit the New Worlds mission, a bold concept that could still redefine how we capture images of distant exoplanets. Proposed in the early 2000s, this mission centered around a revolutionary tool called the Starshade, a massive flower-shaped structure designed to block starlight with pinpoint precision. Imagine holding up your hand to shield your eyes from the sun, except this starshade will be floating tens of thousands of kilometers in front of a space telescope, creating an artificial eclipse to reveal planets hidden in the glare of their stars. What makes the New Worlds mission so groundbreaking is its simplicity. Unlike complex coronagraphs built into telescopes, the Starshade is a separate, deployable device. This means it could pair with existing or future telescopes, turning them into exoplanet imaging powerhouses without requiring costly redesigns. The Starshade's petals are meticulously shaped to diffract starlight away from the telescope's view, allowing it to spot faint Earth-sized worlds that would otherwise be lost in the cosmic glare. Though the New Worlds mission never progressed beyond early studies, its legacy endures. NASA's Habitable Exoplanet Observatory, or HAB-X, and other future concepts are now exploring Starshade technology as a game-changer for direct imaging. The potential is staggering. A Starshade-equipped mission could analyze the atmospheres of dozens of nearby exoplanets, searching for signs of water, oxygen, or even industrial pollutants hinting at alien civilizations. One of the most exciting aspects of this technology is its adaptability. A single starshade could serve multiple telescopes, repositioning itself to study different star systems. Think of it as a cosmic spotlight, moving from one target to the next, unlocking secrets across the galaxy. And with advances in lightweight materials and precision deployment systems, what once seemed like science fiction is inching closer to reality. The New Worlds mission reminds us that sometimes the most elegant solutions are hiding in plain sight. While we await the next generation of Starshade-equipped telescopes, let's turn our attention to an even more mind-bending concept, using the sun itself as a magnifying glass to peer deeper into the cosmos than ever before. Now, let's stretch our imagination even further with a concept that sounds like it's straight out of a sci-fi novel, the Focal Mission, which aims to turn our very own sun into the most powerful telescope ever conceived. Here's how it works. Einstein's theory of relativity tells us that massive objects like stars bend the fabric of space-time, acting like a lens that can magnify distant light. The focal mission would position a spacecraft at the Sun's gravitational focus point, roughly 500 times farther from the Sun than Earth's orbit, where this lensing effect is strongest. At that distance, the Sun's gravity would amplify the light from exoplanets up to 1,000 light-years away, revealing details we could never see with conventional telescopes. Picture this: a world orbiting another star, not as a blurry dot, but as a resolved image where we could potentially make out continents, oceans, or even signs of civilization. The clarity would be unmatched, offering a front-row seat to alien worlds in ways we've only dreamed of. What makes focal so revolutionary is its sheer scale. Unlike building bigger telescopes or launching more advanced instruments, this mission leverages a natural phenomenon already in place: the challenge. Getting a spacecraft to that distant point and keeping it precisely aligned to capture the magnified light. It's a feat of engineering that would require breakthroughs in propulsion and navigation, but the payoff could redefine our understanding of the cosmos. Imagine the discoveries waiting at the Sun's gravitational focus. We could study exoplanet atmospheres in unprecedented detail, searching for biosignatures like oxygen or methane. We might even detect artificial structures or city lights, evidence of intelligent life. And because the Sun's lens doesn't discriminate, this mission could peer into star systems far beyond the reach of any other technology. While focal remains a visionary concept for now, it represents the kind of bold thinking that pushes humanity forward. As we continue exploring the possibilities, let's turn our attention to another ambitious mission, one that aimed to find Earth-like worlds but was shelved, leaving behind a legacy that still shapes our search today. Now, shifting our focus to a mission that never got off the ground but left an indelible mark on exoplanet exploration, the Terrestrial Planet Finder. Originally envisioned as one of NASA's most ambitious projects, the Terrestrial Planet Finder was designed to detect and study Earth-like worlds around nearby stars. Its goal was simple yet profound: to answer the age-old question of whether we're alone in the universe by directly imaging rocky planets in habitable zones. So, why was this flagship mission cancelled? The answer lies in a mix of budget constraints and shifting priorities. In the mid-2000s, NASA faced financial pressures, and the Terrestrial Planet Finder's high costs, estimated in the billions, made it a target for cuts. Technical challenges also played a role. The mission required unprecedented precision in telescope stability and starlight suppression, pushing the limits of existing technology at the time. But here's the good news: the Terrestrial Planet Finder's legacy didn't fade away. Its core objectives live on in modern missions like the Habitable Worlds Observatory and the Habitable Exoplanet Observatory. These projects inherited its groundbreaking vision, refining the technology to make direct imaging of Earth-like exoplanets a reality. The Habitable Worlds Observatory, for instance, will use advanced coronagraphs to block starlight, just as the Terrestrial Planet Finder planned, while the Habitable Exoplanet Observatory's starshade concept builds on similar principles. What's fascinating is how these successors are turning the Terrestrial Planet Finder's once distant dreams into achievable science. By learning from its setbacks, today's missions are more cost-effective and technologically feasible, proving that even cancelled projects can pave the way for future breakthroughs. As we reflect on the Terrestrial Planet Finder's unfinished story, it's a reminder that exploration is as much about perseverance as it is about discovery. Next up, we'll dive into how future missions are tackling another critical piece of the exoplanet puzzle: space weather and its impact on alien worlds. Now, let's turn our attention to a hidden but critical factor in the search for habitable exoplanets: space weather. While we often focus on a planet's atmosphere or distance from its star, the activity of the host star itself can make or break its potential for life. Imagine a world bathed in deadly radiation from frequent solar flares or battered by violent coronal mass ejections. That's where exospace weather missions come in. Future satellites dedicated to monitoring these cosmic storms could revolutionize our understanding of exoplanet habitability. These missions would track flares and coronal mass ejections from distant stars, measuring their intensity and frequency. Why does this matter? Because a star's outbursts can strip away a planet's atmosphere, fry its surface with radiation, or even trigger chemical reactions that make life impossible. One proposed mission could deploy a fleet of small, specialized telescopes orbiting between Earth and the Sun, keeping a constant watch on nearby stars. These observatories would use advanced sensors to detect ultraviolet and X-ray emissions, key indicators of stellar violence. By cataloging which stars are calm and which are volatile, scientists could prioritize the search for life around the most stable systems. Another exciting possibility is pairing these observations with existing exoplanet data. Imagine knowing not just that a planet is in the habitable zone, but also whether its star is a gentle neighbor or a cosmic bully. This intel could help us identify truly Earth-like worlds, not just those that look good on paper. The stakes are high. A planet might have liquid water and a thick atmosphere, but if its star erupts with flares every few days, it's likely a dead zone. Exospace weather missions would give us the tools to rule out these hostile environments, or, in rare cases, discover worlds with natural shielding that defies the odds. As we push deeper into the era of exoplanet exploration, understanding space weather isn't just an add-on, it's a necessity. Next, we'll explore an even bolder idea, using quantum physics to communicate with probes light years away. Now, let's take a leap into the realm of cutting-edge physics with a mission that sounds like science fiction, but could one day become reality: quantum communication probes. Imagine sending data from an exoplanet light years away and receiving it instantly, as if the vast distances of space no longer mattered. This is the promise of quantum entanglement, a bizarre yet fascinating phenomenon where particles become linked, sharing information faster than the speed of light. Scientists are already exploring how this could revolutionize interstellar communication. Traditional radio signals take years or even centuries to travel between stars, making real-time data exchange impossible. But quantum-entangled particles could change that. Here's how it might work. A probe sent to a distant exoplanet would carry a pair of entangled particles, one staying on Earth, the other traveling with the probe. When the probe measures something, say, the composition of an exoplanet's atmosphere, that information could theoretically be instantly mirrored on Earth through the entangled pair, bypassing the need for slow-speed transmissions. Of course, the challenges are enormous. Maintaining entanglement over such vast distances is still beyond our current technology, and even the slightest interference could break the fragile quantum link. But researchers are making progress, with experiments on Earth already demonstrating entanglement over hundreds of kilometers. Scaling this up to interstellar distances would require breakthroughs in quantum engineering, but the potential payoff is staggering. Think about it. If we could receive real-time data from probes orbiting exoplanets, we wouldn't just be studying these worlds, we'd be experiencing them as they happen. No more waiting decades for a single signal, no more guessing based on outdated snapshots. This could open the door to a new era of exploration where distant planets feel almost within reach. While quantum communication remains speculative for now, it represents the kind of bold thinking that could redefine our relationship with the cosmos. Next, we'll shift gears to another game-changing idea: how artificial intelligence is set to supercharge the hunt for exoplanets in ways we're only beginning to imagine. Now, let's turn our attention to a tool that's already transforming the way we explore the cosmos: artificial intelligence. The next frontier in exoplanet discovery isn't just about bigger telescopes or faster probes, it's about smarter algorithms. With a sheer volume of data pouring in from missions like Kepler and TESS, human astronomers are practically drowning in information. That's where machine learning steps in, acting as a tireless cosmic detective that never sleeps. Picture this: every night, telescopes around the world capture countless images and light curves from distant stars. Hidden in that mountain of data could be the faintest dip in brightness, a telltale sign of an exoplanet passing by. But finding those needles in the haystack takes time, patience, and a lot of human effort. AI changes the game by analyzing petabytes of data in a fraction of the time, spotting patterns even the sharpest-eyed scientists might miss. Already, projects like Google's AI have uncovered new exoplanets in old Kepler data that humans overlooked. But this is just the beginning. Future missions will deploy machine learning not just to find planets, but to classify them, predicting their size, composition, and even potential habitability based on subtle clues in the data. Imagine an AI that can instantly flag an Earth-like world from a sea of gas giants, or detect the faint chemical fingerprints of water or methane in an exoplanet's atmosphere. The beauty of AI is its ability to learn and improve. The more data it processes, the better it gets at distinguishing real planetary signals from false alarms, like star spots or instrument glitches. And as missions grow more ambitious, AI will be essential for handling the flood of data from next-gen telescopes like the Extremely Large Telescope or the Nancy Grace Roman Space Telescope. But here's the most exciting part. AI could one day discover planets we didn't even know to look for. By identifying anomalies or unexpected patterns, machine learning might reveal entirely new classes of exoplanets, worlds that defy our current understanding of planetary science. As we stand on the brink of this data-driven revolution, one thing is clear: the future of exoplanet hunting isn't just about looking farther, it's about seeing smarter. And with AI as our guide, the universe's secrets may unfold faster than we ever imagined. Up next, we'll explore another bold idea: a fleet of tiny satellites working together to verify the most tantalizing clues of alien life. Now, let's take a leap into the future with a mission that could finally answer the ultimate question: are we alone? Imagine not just one spacecraft hunting for signs of life, but an entire fleet working in perfect harmony. This is the vision behind Mission 29, the Biosignature Verification Fleet. Think of it like a cosmic detective squad. A single telescope might spot what looks like oxygen or methane in an exoplanet's atmosphere, hints that life could exist. But what if that signal is a trick of the light, or some weird geological process we don't understand yet? That's where this swarm of microsatellites comes in. Each one would double-check the other's findings, analyzing the same planet from different angles with different instruments to separate real biosignatures from cosmic false alarms. These wouldn't be bulky, expensive probes. Picture tiny, affordable satellites no bigger than a shoebox, launched in waves to study promising worlds. Some might focus on atmospheric chemistry, while others monitor surface temperatures or scan for unusual light patterns. Together, they'd build a rock-solid case for life by ruling out every other possibility. The real game changer: speed. Instead of waiting years for follow-up observations from Earth or a single flagship telescope, this fleet could deliver answers in months. Imagine confirming an Earth-like world has oxygen, water, and even chlorophyll-like pigments, all before the next mission even launches. And here's the kicker: this approach doesn't just reduce errors. It could uncover life in ways we haven't even thought of. By cross-referencing dozens of data points, the fleet might spot subtle patterns invisible to single instruments, like seasonal changes in gas levels or surface features that hint at alien ecosystems. Of course, coordinating a swarm across light years won't be easy, but with advances in miniaturization and AI, this could be the most reliable way to shout, "We found them," without later having to take it back. After all, when it comes to discovering life beyond Earth, we'll want to be absolutely certain. Up next, we'll push the boundaries even further. with concepts that sound like science fiction but might one day carry humanity to the stars themselves. Now, let's venture into the realm of science fiction turned potential reality, where humanity's boldest dreams of reaching the stars take shape. Mission 30 brings us to the cutting edge of interstellar travel with concepts that could one day carry entire civilizations across the cosmos, interstellar arcs. Picture this: a colossal, self-sustaining vessel drifting through the void for centuries, maybe even millennia. Inside, generations of humans live, work, and thrive, all with one ultimate goal: reaching a habitable exoplanet to call home. These aren't just ships, they're mobile worlds equipped with everything needed to sustain life indefinitely: farms, water recycling systems, even artificial gravity to keep bones and muscles strong. But here's the twist: some designs go beyond carrying human passengers. Imagine seed ships, robotic arks packed with frozen embryos or synthetic DNA, ready to rebuild humanity, or even entirely new ecosystems on a distant Earth-like world. No need for fragile human crews, just advanced machines that could awaken and begin terraforming upon arrival. The challenges, they're as massive as the ships themselves. How do you keep a society stable and motivated over centuries of travel? How do you shield passengers from cosmic radiation or the psychological toll of isolation? And perhaps the biggest question: how do you ensure the destination is still habitable by the time you get there? Yet, with breakthroughs in propulsion, closed-loop life support, and AI, these ideas are inching closer to feasibility. Projects like Breakthrough Starshot might get us data from nearby stars in decades, but interstellar arcs could deliver something far more profound: a future where humanity isn't confined to a single pale blue dot. This is where science and imagination collide. Whether it's a generation ship nurturing hope across the light years or a seed ship silently carrying the blueprint for life, these concepts remind us that the universe might one day be within our grasp. And with that, we've journeyed through all 30 missions, each a stepping stone toward unlocking the secrets of distant worlds. So tell us, which vision of the future excites you the most? Drop your thoughts in the comments, and don't forget to like and subscribe for more deep dives into the cosmos. The adventure is just beginning. As we wrap up this cosmic journey, let's take a moment to reflect on the incredible potential of these 30 missions. From the Habitable Worlds Observatory's quest to capture the first direct images of Earth like exoplanets, to the daring vision of interstellar arcs carrying humanity's future among the stars, each mission represents a leap forward in our understanding of the universe. Together, they paint a picture of a future where the mysteries of distant worlds are no longer out of reach. These projects aren't just about discovering new planets, they're about answering humanity's oldest questions. Are we alone? What makes a world habitable? Could life thrive under alien suns? With advanced telescopes analyzing atmospheres, tiny probes racing to nearby stars, and even the dream of generational ships, we're closer than ever to finding out. The next few decades will redefine our place in the cosmos, and every mission we've explored plays a part. Whether it's uncovering biosignatures with LUVOIR, mapping exoplanet climates with Ariel, or pushing the boundaries of speed with Breakthrough Starshot, the possibilities are as vast as space itself. So now it's your turn. Which of these missions sparks your imagination the most? Is it the high-tech hunt for alien life, the bold plans for interstellar travel, or something else entirely? Drop your thoughts in the comments below. We'd love to hear which vision of the future excites you. And if you enjoyed this journey through the cosmos, don't forget to like, subscribe, and hit the notification bell so you never miss out on the next adventure into the unknown. The universe is waiting, and the discoveries are just beginning.